Okay, so we now move to the downsampling part. So we have already looked at the expansion or the case where we have upsampled. The second case where we mentioned yesterday that when I do sampling rate reduction, there is a possibility of loss of information. That is the one that we want to keep in mind, and that is what we are going to focus on in today's lecture. So the downsampler, opposite of the upsampler is the downsampler, opposite of the interpolation is decimation. So we will just call it either as a downsampler or as a decimator. The notation that we follow is a box with a down arrow with value equal to m. If this is x of n, we call this as xd of n, that is equal to x of mn. Okay, and this we have already looked at in the time scaling part. So nothing new or difficult in this one. The important thing that what we would like to develop in today's class is the representation of xd of z. Obtain the z transform or the frequency domain representation of the downsample signal or the decimated signal. So that is the goal for today's lecture. Okay, so before that, what I would like to do is a notion of what is called stretching in frequency. Okay, so the word stretching is a layman's term, but it is useful in terms of visualization. Stretching of frequency. Okay, again let me just explain what it is and then allow you to find a way to associate what it means when you say stretching of spectrum and what does it actually do. Okay, now supposing I have a band limited signal, with the highest frequency component as 5000 hertz. Okay, so if I were to show in terms of the spectrum, this is 2 pi times 5000, this is the continuous time frequency, and this will be minus 2 pi times 5000. Okay. Now I sample it at the rate of 40,000 hertz. Sampling frequency is 40 kilohertz, 40,000 hertz, the sampling period is 1 by 40,000. So if I were to now translate this into the discrete time domain, basically 2 pi corresponds to 40,000. So 5000 is 1 by 8 of that. So this will correspond to pi by 4. So the discrete time spectrum for this signal is minus pi by 4 to pi by 4, and then this spectrum will repeat at 2 pi. Am I right? That is a straightforward sampling representation. Now do the following. If you now change the sampling frequency to fs dash equal to 20 kilohertz, okay, what happens to this one? The drawing now becomes, basically it becomes twice as wide. It goes from minus pi by 2 to pi by 2, and the spectrum here also is 2 pi, this is 3 pi by 2 and pi. Okay. Now the signal did not change, the same input signal. I changed the sampling frequency, I reduced the sampling frequency by a factor of half. The discrete time representation seems like the spectrum has been stretched. Whatever was the input spectrum at when I did the sampling at 40 kilohertz, when I do it at 20 kilohertz, the spectrum is wider. Now why is it, why does it look wider? Because the sampling frequency is now smaller. With respect to the sampling frequency, my highest frequency component now looks a larger fraction, and therefore it looks, so if we always tend to draw 0 to 2 pi. When you draw 0 to 2 pi, it looks like my spectrum has stretched. So this is what we mean by stretching of the spectrum. The signal did not change, nothing has changed about the actual signal or the signal contents, but the representation looks different, one looks like there is a stretching, and this is what will come into play whenever we do the changing of the sampling rate, and that is where it is very important for us to keep in mind. So, the stretching of spectrum, I hope you will, if you have a doubt, you will be able to just come back and take a look at this example and then say, okay, now what exactly is happening and why is it happening, and be able to explain it in that fashion. Now, we move into the actual derivation of the xd of z, xd of z. Again, the underlying fact is that I am reducing my sampling rate. Reducing my sampling rate, I already know a couple of things. My spectrum will stretch, that is a stretching in frequency. The other element is there is a possibility I am losing, in the process I may lose information and therefore introduce some ambiguity. So, there is one example that I would like to show you, and it is a standard example when we say that what happens when you have aliasing as present. So, if this is the continuous time signal and I sample it at the following points and I get the following expression. Okay, these are the samples that are obtained. Again, this is the sampling process, and this is something that we are well understood. This is uniform sampling at a given sampling rate. Now, if I have downsampled this signal by a factor of 3, so that means this sample remains, this remains, this remains, this remains, and this remains. Those samples, the others are not there in my. So, in other words, my samples now are this, 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 and this. Okay. Now, here is the example and its illustration. Now, if I had, for just as a case study, now if I had a continuous time signal that was given by this blue graph and it had been sampled, I would have gotten the same samples as if I had had the green line and sampled it at this rate. Now, when I am given only the samples and asked to reconstruct, what I am most likely to reconstruct is something that looks like the green line, because I do not have enough information to reconstruct the blue line. So, in other words, the minute I have thrown away samples, there is a risk that I may not be able to recover the original signal, and here is a classic case where if I had had all of the samples, I would have reconstructed even the blue line, I mean assuming that the samples were present, but the minute I go down to a lower sampling rate, I may have lost that information. So, this is where the underlying notions of aliasing come in. Aliasing basically means that I am not able to reconstruct the original signal. I do not have enough information to reconstruct it. No aliasing means that I have satisfied Nyquist, which means that I have sufficient information to reconstruct the original signal. So, with this in mind, basically I would like to now write down xd of z is summation n equal to minus infinity to infinity xd of n z power minus n. Basically the standard Z transform representation. So, this is n equal to minus infinity to infinity x of mn z power minus n. Okay. I have just substituted the expression for the time scaling in the discrete time. Now, it is actually difficult for us to proceed beyond this point if we do not define some other sequences that will help us. So, we are going to define an intermediate sequence, and you will find that this is probably one of the most interesting and useful insights in the whole discussion today. So, there is an intermediate sequence which may not seem like very useful, but it actually turns out to be very, very valuable. The intermediate sequence, we will label it as x1 of n. This is equal to x of n if n is equal to a multiple of m, plus minus 0 or 0 plus minus m plus minus 2m and so on, equal to 0 otherwise. Okay. It actually has less information than x of n. Why not? Might as well have worked with x of mn, because that has the same information, but actually this sequence has a lot of value and benefit. Now, I would like to go back and look at xd of z. So, xd of z is equal to x of mn, that is equal to x1 of mn, correct. Now, you may see that, well, it is even less we can't, it looks like it's even less useful. So xd of z is equal to summation n equal to minus infinity to infinity x1 of mn z power minus n. Probably not seeing any benefit at all of having defined x1 of n except the following. Now I would like to do a change of variable mn equal to k. Please note I am going to do going to change the variable, and this is going to be a very important step. So k going from minus infinity to infinity x1 of k. Now you may say wait a minute, because the previous summation took only the multiples of m. Now you are saying I am going to run over all the values. I did not lose any information, because notice that x1 of n has got zeros at the other points. I can run my summation over all the indices, over the entire set of indices. So this is very important, this step is important. So if I am running my summation over this variable k, which is equal to mn, then z power minus n will come out to be minus k over m. It is a modification of that, and this is if x1 of z is equal to summation k equal to minus infinity to infinity x1 of k z power minus k. If this is the general definition of x1 of z, then I now have an expression for xd of z. xd of z is nothing but x1 of z of 1 over m. It is a very interesting and important result, because this is like the counterpart of the zero insertion, because what happened in the zero insertion, your the upsampled signal had a scaled version of the spectrum of the input. Now this one says that, okay, it is not the input itself, but it is some intermediate sequence which has got a factor of 1 over m. Let us quickly take a look at what does this scaling by a factor of 1 over m. Previously we looked at what happens to a scaling when you have a scaling of L. So if xd of E of j omega we said is equal to x1 E of j omega by m, okay. So now this is where you will see the stretching of the frequencies, because if I take an omega equal to pi by 6, okay, omega equal to pi by 2 for xd E of j omega, this will correspond to x1 e power j pi by 6, right, because whatever was the original frequency I have to divide by 1, and if I take the case where m equal to 3, if I take m equal to 3, then the relationship between the frequencies of the xd and this one are, so if I were to show it in terms of a spectrum, I am going to show only from 0 to pi. So again, do not be confused by what we are drawing. So if I am going to draw a signal that goes from minus pi by 6 to pi by 6, okay, this is for x1 E of j omega. This is purely for illustrative purposes. If I have a spectrum that looks like this, then xd is going to be the same thing stretched by a factor of 2. It will go from minus pi by 2 to pi by 2. This will be xd E of j omega. So basically this notion of stretching in frequency, when I reduce the sampling rate, there is a stretching in frequency that will come, that is very important for us. It is linked to the stretching in frequency that I described at the start of the lecture. Again, this is an intermediate step. I have defined a new sequence. This sequence has got lots of zero valued samples, and it is related to the downsampled signal xd of n using the same relationship, and it gives us a closed form expression for the z transform of xd of z. Okay, this is still not the final answer.
If we give it for given x1,
yeah,
we lose the periodicity of 2 pi for xd. Right?
Exactly. So very important point. When you have xd E of j omega by m, okay, what is the periodicity of that? It is m times 2 pi. So now can you have a discrete time signal which is not periodic with 2 pi? No. That is why I said you have to be very careful in interpreting this this expression. Okay. So, this was shown only to tell you that in the range from 0 to pi by 6 you will actually have a stretching of frequency. So, if I actually had to draw e power x1 e of j omega by m or x d e of j omega, I would actually have to draw from minus 2 m times 2 pi to m times 2 pi. Okay. But the periodicity of x d is still 2 pi. So, that is why I did not want you to get confused with the scale, but yes, whenever you have a scaling like this, the original function had a frequency period equal to 2 pi. Now, by design it will have a period to m times 2 pi. Okay. But we will not violate any of the fundamental principles, and that will come out in the next portion, the rest of the lecture. Okay, I am glad you asked that question, because that is a very important one, and it is something that actually is one of the important elements we should not miss in this discussion. Okay, now how do I relate x1 of n and x of n? What is the relationship between these two? Basically, I have set some of the values to 0, okay, and we can think of the following. We can define a comb sequence. C stands for comb, n is a time index, m stands for the where the comb occurs. So, the comb frequency comb sequence is 0, then it has got lots of 0 valued samples, then at index m there has got a 1 and then some 0 valued samples, at 2m it has got. So, basically this is a comb sequence, right, with the subscript index 1. So, these are samples of height equal to 1. So, if I multiply x of n with this comb sequence, then I will get x1 of n. Okay. So, that is a interesting observation. So, in other words, the way I set the sum of the samples of x of n to 0 is by multiplying the original sequence with the comb sequence, which will take care of it. So, comb sequence definition, this is equal to 1 if n is equal to a multiple of m, equal to 0 otherwise. So, it basically sets all of the other samples to 0. Okay. Now, how do I construct comb sequences? Very easy. Complex variable theory gives us a very useful result. I am sure you would have used it. The m complex roots of unity, m complex roots of unity. What are they? Alpha k is e power j 2 pi over m times k, correct? And so, basically I can take any of the roots of unity. Let me take alpha 1, that is e power j 2 pi over m, and then I can write down the following equation: 1 plus alpha 1 plus alpha 1 squared all the way to alpha 1 raised to the power of m minus 1, that is equal to roots of unity. When I take the powers of root is equal to 0. Thank you. Basically, you will do a geometric series and show that numerator goes to 0. So, therefore, you get this expression. Okay. Now, if I look at the following, 1 plus alpha 1 raised to the power n alpha 1 raised to the power 2n plus alpha 1 raised to the power of m minus 1 times n. This is still equal to 0 if n not equal to multiple of m. However, if n is equal to multiple of m, then all of these roots of unity will be equal to 1, and therefore, then it becomes equal to m if n equal to a multiple of m. Okay. So, now you can see how the comb sequence more or less emerges from this discussion, and so we say that the comb sequence Cm of n, I do not want the summation to be equal to 1. So, I add a 1 over m to normalize it, summation k equal to 0 to m minus 1 e power j 2 pi over m times k times n. Okay. That is basically relating it to this equation. Okay, so that will tell me that I will effectively get a comb sequence. Now, when you study DFT, you would have introduced the following notation: W subscript m, that is e power minus j 2 pi over m. And it's a very useful notation from there. So the comb sequence can be written in terms of the DFT coefficient W in the following form: it's equal to 1 over m summation k equal to 0 to m minus 1 W subscript m minus kn. Okay, because of the definition of Wm, there is a minus sign that comes in the exponent of this. Okay, and this you can verify, this is equal to 1 if n equal to a multiple of m and equal to 0 otherwise. So this is the comb sequence, what a very compact representation. So x1 of n is equal to x of n multiplied by the comb sequence, this class. Okay, so basically multiplication by the comb sequence. Now I want to evaluate x1 of z. So far I did not do that. Let me evaluate x1 of z. This is basically summation n equal to minus infinity to infinity x1 of n times z power minus n. x1 of n, I substitute the other expression. So this is summation n equal to minus infinity to infinity x of n. I have to multiply by the comb sequence. The comb sequence is 1 over m summation k equal to 0 through m minus 1 Wm minus kn times z power minus n. Okay, this is nothing but the comb sequence. Okay, this is Cm of n. Okay, now just the last step, and I will pick it up from here in tomorrow's lecture, but just wanted to leave this as the last point. So x1 of z, if I interchange the summations, I would like you to show that this comes out to be 1 over m summation k equal to 0 through m minus 1 x of z w k. So this equation I would like you to interpret using the following. One, there is a scaling. This is a scaling, amplitude scaling. Okay, there is an amplitude scaling. The second one, there are copies of the signal, multiple copies. How many copies? M minus 1 additional copies. And the third is that this basically means that they are frequency shifted. The copies are frequency shifted, and frequency shifted by what? They are shifted by 2 pi over m times k. Okay. So there is a scale factor, and then there are shifted versions of that. So please interpret this equation, and we are one step away from writing the expression for xd of z that we will complete in tomorrow's lecture. Thank you.